thank you to give me this spot to keep you updated on what we are doing now in CheckMATE. So I will first give you a brief introduction of what is CheckMATE and a bit of promotion of the code. Then I will explain what we are doing lately. And finally, I will give you an example of use of CheckMATE that maybe motivate you for using it. So what CheckMATE? CheckMATE is a tool for casting arbitrary models. So the idea is that if you're a theorist or a phenomenologist and you want to check if your preferred model is excluded for a particular point or not, you can come to this tool and you can use different types of input information. You can just simply, for example, take your UFO files of your model and some spectrum file and some process, feed it to CheckMATE, and it will calculate the Monte Carlo events for you with markup, then hadronize with PCA, or you can directly feed the hard events in LHI format or the hadronized events in HEP-NC format. And finally, CheckMATE will do internally the detector simulation based in Delphos, and it will classify the events in the different signal regions of the searches that are recasted inside of CheckMATE. And it will give you an answer on how this number of events on each signal region compared to the upper limit for each of the signal regions and tell you if your model is excluded or not. So the idea is that you can take your, without a lot of knowledge about how the code works and not very high computer resources, you can take your preferred model, come here and test it against LHC searches that were not originally designed to look for your preferred model. The main branch of CheckMATE is intended to work in searches for prompt particles, but there is a separate branch that can handle searches for long-range particles. We have many ATLAS analyses already implemented at 13 TeV energy, but we also have some, if you are interested, at 7 and 8 TeV of energy. And we also have some searches which are the projection from the experimental collaborations to high lumi that you can check also in CheckMATE. We have a more humble list from CMS that is increasing. We're working on putting more searches from CMS. And let me now pass to what we are doing now. So the main branch from CheckMATE, traditionally what it does is calculate the limits based only on the information from the signal region with the largest expected sensitivity. This is good if you don't have access to the statistical model that the experimentalists are using. But the bad part is that you are not using all of the available data, so you are going to, for sure, lose sensibility. But thankfully, ATLAS and CMS have provided enough information to reconstruct the statistical model. In the case of ATLAS, they are publishing in HEP data, as they explained before, the full statistical model in JSON format. And also they provide a prescription of how to build a simplified statistical model, taking all of the background information in one single sample. And CMS is giving instructions and information about a simplified model using the information from the covariant matrix that is enough, again, to reconstruct with good accuracy the statistical model. So what we do? In the case of ATLAS, we based on PyChef an implementation of the combination of information from different signal regions. Most of the searches that we have implemented so far have the full likelihood published, but there are some that don't. In this list that is fully checked, there is one that doesn't have the full model published. So automatically, CheckMATE is either taking the workspace from HEP data and feeding it to PyChef, or building inside PyChef another workspace only with the simplified approach. Then by default, CheckMATE is calculating an upper limit on the signal strength of the process you are selected for your model, making a scan over the parameter of interest. And this in general works fine, but for some of the searches, the statistical model is quite complicated, and in a small computer and a laptop, it can take a very heavy workload. For example, this search for quarks and gluinos that have around 60 bins our experience is that a laptop can take around 20 hours to find an upper limit on the signal strength. So this is not practical clearly for a theories approaching this tool. So we also give the option of, instead of making the full scan for the upper limit, to calculate only the CLS for this specific point you're fitting. And also you can always just drop the full model and calculate with the simplified model that in general works in a reasonable amount of time. We are also implemented control regions in the recasting analysis. We have already now for this the Squark and Gluino search the control regions. So when you load the full model, the information of the number of events that are predicted in the control regions is also fit in the model. And in the case of CMS, since at least in the moment where we were implementing this, PyChef didn't have the option to load the covariant matrices. I don't know now. So we started by building a workspace based on PyRoot. We have something that works, but to be honest, the performance is far from optimal. Maybe it's us to blame for that, because we build that based on the manual and the examples that are on the webpage. So maybe there is a better way to do that. But very often the calculation is not converging properly, and it's giving nonsensical results. Our suspect is that the problem is that the CMS search has a large number of bins defined in most cases. And since with this tool, we're intending to have a simulation that you can write in your laptop, normally the number of events that you include in your Monte Carlo is not very large. And you end up with an array of results that is very sparse, with large relative errors in some of the bins. And probably this is far from optimal from the numerical point of view for the minimization of your likelihood. So we're trying different approaches. One option is to change the treatment of the signal prediction and promote it to a nuisance parameter that is also constrained with exponential. And also we try another approach, which is changing the optimizer. We use another tool, probably you already know, SPAY, which is also Python based. This one can take covariant matrices, shows very good stability compared with the root implementation, and where both converge properly, the results have good agreement. So other features we're trying to test now is the possibility to combine the results from different searches. Of course, this has to be made with casual, but we can offer these options to the user, and the user can decide if this makes sense or not. And in an understanding of the CMS published information, there is some ambiguity on how the background errors are defined. So there is some flexibility on how aggressive to be in the treatment of errors, and we're working also on that. Maybe with some more input from CMS, we can understand better what we are doing. But I can show you some examples of the searches that we have already validated. So this is first, this is the ATLAS search from Squark production. They came fully hadronically. The red and yellow colors means the official ATLAS limit. And here you can see the comparison between the kind of limits you obtain using the old approach of CheckMATE, only using information from one signal region, and combining information of different signal regions using the simplified likelihood. So the orange line will be the limit based on a single signal region, and the red one, the green one, will be the one obtained with the combination. This is the same plot, but instead the orange line now is using the full model download from HEP data. As expected, the simplified likelihood gives more sensitivity than the single signal region, but here it seems like using the full model, at least to us, shows that maybe the simplified likelihood in this case is overshooting the sensitivity. Maybe this depends from search to search, I don't know. This one corresponds to CMS. This is the same kind of target signal. This again, the Squark production became fully hadronically. Red line is the official CMS limit, and the blue line is the limit obtained when we build the the simplified likelihood using the covariant matrix. We have many other searches already tested with different kind of final states. We have here, for example, with BDJets in the bottom per production, with tau hadrons in the tau per production, with leptons in the compressed lepton scenario, or with the gluino pair decay to jets, missinity, and leptons. This is the fully hadronic decay of tau per production. We have many others already implemented and tested. So performance is in generally good, but it's not perfect. Some cases show that there is some difference between what we obtain really and official limits. So it's not catastrophic, but well, it is what it is. And also for CMS. So again, this one is gluino pair decay to top quarks. And here is the monojet search testing the simplified model with a vector mediator. So let me now give you an example of how to use this for some theory model. So this is a very popular model, is supersymmetry in the case where only dark matter is accessible. We select the Gaussianos or Higgshinos to be dark matter. We decouple the rest of the spectrum and consider three scenarios. One, when Bino Winos are light and almost degenerate in mass. The second, only with the Winos. And the third one, only with Higgshinos, with mass gaps between 100 and 1,000 MeVs. Motivation for this model could be, for example, that you achieve correct relic density through co-annihilation. And in this with this kind of degeneracy between the states, it's not possible to see the decay products of the heavier states to the lightest one. So your only chance to see these at colliders is to include in the production of the event also initial state radiation and try to see an event of the form of missinity plus some jets from ISR. So these kind of models are tested at LAC in different forms. Typically, for example, is the search for disappearing tracks. If your charge state is too compressed with the LSP, the decay length is very suppressed kinematically, and it can travel a significant distance within the collider before decaying. And you can actually see a charge track that is disappearing inside of the detector. This can put important limits, and this region in yellow here that is already excluded. Also, if you had a heavier neutral state, like in the case of the Bino model or in the Higgsino model, the neutral state can decay through a very offset set boson, gives you a very soft pair of leptons. And still you can see these leptons and make some kinematical gain to disentangle from backgrounds, and you can put some limits over these models. This is the blue region that is excluded. And finally, there is a long-standing limit from left that excludes the electroweakinos more or less about 100 GeVs. But there is a gap here in the middle that is not covered from any of these options. And our idea is to test these models in this gap with the idea of confronting this model with searches for jets and missinity. Cross searches that were not initially designed for this kind of signal. So we select first the ATLAS search for squares and gluinos. This is the one which result I presented before. This includes this new feature of making a multibin fit over a set of orthogonally defined signal regions. Have the corresponding CMS search for squares and gluinos, decaying fully ironically. Selections are not exactly equal. There is some difference that are important for the signal testing here. In particular, this is shown here, probably not. But ATLAS is rejecting events where the separation between the jets and missinity is not very large, and I think CMS is not doing such a thing, and it's not that much. The result here is in the left panel from ATLAS. One can see that, for example, in the model for Winos could be excluded up to around 160 GeVs. And in the case of CMS, exclusion is a bit harder, and especially it goes to higher mass separations, because in the case of ATLAS, when the hadronic decay of the winners start to be resolvable at LHC, then the extra hadronic activity going in the direction of the missing ET can destroy the selection process of ATLAS. While in the case of CMS, it's not such the case, and you can see that the sensitivity goes to much larger mass separation between the winners. So just to summarize a bit, we are preparing a new release of CheckMATE. The idea is that it will include the calculation of upper limits based on the combination of information from different signal regions. This implementation is based on PyCheck for ATLAS and in root or space for CMS. In most cases, it runs fine. It runs fine and smooth and in a reasonable amount of time. But for some searches, it can have be more demanding in terms of computer resources. So you can we give the option to the user to change the kind of calculation he's doing to save time. And we are finding some problems with the implementation in root with CMS, but at least up to now, we are for the searches we are testing, we are able to work around the problems and have some searches that are actually working. So the agreement with the ATLAS and CMS results is reasonable, and hopefully in the future you can test your preferred models with this new implementation CheckMATE. And we have already some results published in terms of the electroweakinos that are promising in terms of what you can do with this tool.
Thank you very much. Okay, so we'll go to Zoom first for questions. If you can raise your hand if you have any. Okay, so Sabina, please go ahead.
Okay. Yeah, hi, Christoph. Very nice talk. I was wondering about the validation plots that you showed, where you have quite some discrepancy with the full statistical model, especially for the spot-on to multi-bottom analysis, and also for the Stau analysis here. Yes, because we did the same kind of exercise with models and also with model analysis, and we don't see these discrepancies, especially for the spot-on pair production. We have a very good agreement with the official ATLAS result.
I think that the problem here is probably not with the implementation with PyCheck, because this one is from ATLAS, is probably with the simulation. I think I checked the prediction of on the individual signal regions of the number of events, and I think in the case of this bottom, the V tagging seems to be a bit off. I discussed this with Christoph, and maybe we go a bit deeper in the future into that. But I'm definitely sure this is not a problem with a combination of the signal regions, but probably with the simulation of the classification of the events. I think in the case of the Stau reproduction, I'm not that sure, but it's probably also from this stage the problem.
Yes, the Stau analysis uses a machine learning tau tagger, which you basically can't reproduce. So yeah, this is also difficult. But I think that this kind of plots in this context is a bit misleading, because it looks like the full statistical model performs worse than a simplified approach, which is not true.
Thank you for comment.
Well, the S bottom here at the top left, that's actually 3 regions. This was so how did you combine the regions? Are you doing stitching? Because at the top left here, it looks like you're not actually stitching the regions.
In the top
left. But
the top left, or this bottom. Sorry, what do you mean?
Well, because for that particular analysis, there's 3 regions. And the regions are A, B, and C, and they're split up by mass splitting or something. But you're supposed to be doing stitching here in order to get the contour that you see in the red. So it doesn't look like you actually did any stitching for the region. That might explain the discrepancy.
Okay, maybe, yeah.
Let's see. Okay, so we've already, I've already talked with you a little bit about this at pre-interpretation forum and stuff, but so it seems that in this presentation that this is maybe like some additional motivation for people to get busy working on HS3, because I could imagine that if I mean, I'm obviously not trying to tell CMS what to do or, you know, try and guess at what their plans are, but it would seem that if we were able to get HS3 adoption into combine, then there might be like a road forward towards publishing models for CMS, and that might make this significantly easier for you all as well. So, yeah, so that might be some interesting things to follow up on.
So I wanted to ask, you mentioned on the other side that you are using SPAY. So why don't you use SPAY as well for the PyCheck stuff? Because there is a PyCheck interface for SPAY, and it might simplify your interface overall and just rely on SPAY only.
We have used it for some examples because we actually find some problems with PyCheck for some of the searches where the number of observed events is very off with the background expectation. And if we feed we use PyCheck as a backend for likelihood evaluation, but then use SPAY for the minimization. It seems to be working better than using PyCheck itself. But this is something that we were doing like very lately. So our initial implementation of all of this was initially based only on PyCheck, and that's why we are still relying on this. But it's true that maybe if not completely changing to use SPAY by default, maybe giving the user to change between different options and see what works better and faster or accurate is good, a good option.
Yeah. But yeah, that'd be interesting to follow up more on kind of what's the difference there. Yeah, I mean, we'll have a talk from Jack later today, so we might be able to discuss that more in his section.